Welcome to the online causal inference seminar. Today we're very lucky to have Sara Magliacane from the University of Amsterdam and MIT IBM Watson AI Lab. She's going to talk about, actually the title here has been updated. It's domain adaptation by using causal inference to predict invariant conditional distributions. We also have Tom Klaassen, Joris Moy, and Thijs van Omen in Q&A, and our discussant will be Dominik Rothenhäusler. Guillaume's going to be handling Q&A, so I'll hand it over to Guillaume.
Thank you, Michael. As Michael mentioned, we are lucky to have Tom and Thijs in the Q&A. So they will be answering your question. Tom already did that a while back, and he did a great job. So expect good answers. We will also select a few questions to ask live to Sara. We'll probably keep the questions for the end, but feel free to ask them nonetheless. If your question is selected, I will ask you to raise your hand and I will unmute you. So please do not raise your hand until I've asked you to do so. All right, that's it from me. Sara, whenever you're ready.
So let me share the screen. Okay, it works, right? Okay. So I think I'm supposed to say, may the 4th be with you as first thing. And then I wanted to talk about our work on domain adaptation by using causal inference to predict invariant features, essentially. Oops, sorry about that. Just a second. Okay. And this is joint work with Thijs, who's here, Tom, who's here, Stefan Bongers, Philippe Verster, and Joris Moy, who are not here at the moment. And I'll start by first talking about essentially the general context. And the general context is what can ideas from causality do for machine learning? And I think this is a bit like preaching to the choir, but we know that real world machine learning needs to deal also with biased data. So fairness, selection bias, generalization, heterogeneous data, small samples, missing data, not IID data. And it usually is requiring actionable insights. So you want to make decisions based on the data. So and this is not something you can make with correlations. And again, preaching to the choir, we know that causal inference can actually help with some of these questions. And especially, there are several ways to do systematic data fusion and reuse with biased data and not IID data. And especially, there is a systematic way to extract something I call actionable insights. So insights which allow us to make decisions. But in this talk, I'm arguing like a bit of a middle position. So I'm arguing that full causality sometimes is not necessary. And as people who have worked on it know, it can be too expensive, both computationally and sometimes also just in the collection of data and experiments. And so instead, I'm interested in something in the middle, which I've been calling causality-inspired machine learning. And I think several people have been starting to look into this domain. And especially in this talk, I will just talk about one example, and I will talk about unsupervised domain adaptation. So I'll start with like a general context of how transfer learning and causal inference are connected. So in general, in transfer learning, we're interested in answering the question, how can I predict what happens when the distribution changes for my model? For example, like I have a self-driving car that I have trained in the US, and I would like to also apply it in the UK, but I need to be aware that in the UK, people drive on the other side of the road. So I need to be able to adapt my model to this different setting. And in causal inference, arguably, we want to answer a very similar question, which is how can I predict what happens when the distribution changes after an intervention? And generally, people talk about perfect interventions. So that's like something that is very well treated in the do calculus from Perl. But in this talk, I'm mostly interested in a soft intervention. And in this case, it's essentially the distribution of a variable x that is intervened on, given its parents, changes. And arguably, this can model almost any type of change in distribution. And so we're not alone in thinking about these ideas, and we're also not the first. So as far as I know, this is one of the first papers that I found on connecting causality and transfer learning, covariate shift, concept drift, etc. So, and this is from ICML 2012. And since then, I think there has been a lot of work on this topic. So I start now by introducing some notation I'm going to use just so that maybe it's a bit clearer what I'm talking about. So first I define what domain adaptation is. So let's assume we have some data, so some features, X of I, and we have features X and labels Y, and we have several samples in possibly several types of the source domains. And so they're distributed according to some distribution P of S. In each of the domains, there is a different P of S. And then we have a target domain. And in general, in the target domain, we again have the same features and the same labels, but they're distributed according to a different distribution P of T, which is different from the source domain or the potentially several source domains. And in general, the idea is how can I predict a label Y in the target domain by also using information from the source domain. So this is domain adaptation. And specifically here, I'm talking about the more complicated type of domain adaptation, unsupervised domain adaptation. So essentially it's like a zero-sort learning, if you want. So there are no labels in the target domain. We only have the features X distributed according to P of T and no Y in the target domain. And so how do we work in this setting? And maybe to give you like a more kind of concrete idea, I'm giving here some running example I have with mice, because this is what we use in the paper. So on the left, we have, let's say, some wild type mice, so mice which have not been genetically modified. And we have measured features X1 and X2 and the outcome Y for each of the mice. And each mouse is a row in this table on the left. And then we have genetically modified mice, in which a certain gene A has been knocked out. And for each of them, we do have the features X1 and X2, but we never see the outcome Y, and we want to predict it. And in order to predict it, we want to use essentially what we know from the normal mice, but we know that the distribution is not the same. So how do we do it? So in general, we cannot do it. And so in this talk, we will have to make some assumptions. And so one of the things we're going to use, we're going to represent domain adaptation. We're going to see it from a graphical perspective. So we will have essentially these two data sets with samples from these two distributions. And then a simple thing we can do is we can add a variable D, which just represents the domain. So which data set do the mice come from? And then we can put the data together and consider them as coming from a single distribution, P of X, Y, and D. And then we can represent, we could represent these samples with a causal graph that puts together the two distributions. And this graph is potentially unknown. So this is how we will see this problem. And so again, this is not an idea that we had. So this is an idea that Kun Zhang and others have already described in 2013. And the way they use it also to reason about essentially different assumptions which are very common in transfer learning. For example, a very common assumption is the covariance shift assumption, which assumes essentially that the variable, the label Y is independent of the domain indicator given all of the features X. And there are also other types of assumptions. So now in order to maybe explain why am I talking about independencies, we have the graph, what do independencies, how they are connected. I'm going to just give a very, very quick and very simplified version of this separation. So the separation is a concept which started in Bayesian networks and it's using causality. And it's a concept described, among other things, also in the causality book of Pearl. And the idea is it's a graphical criterion, which under certain conditions allows us to read from a graph the conditional independencies, which will show up in the data. And so the conditions that are used are, so this is a bit technical, there are two conditions. There is a causal Markov assumption and a causal faithfulness assumption. But the idea is that these two together, which is the way they're usually used together, they would assume essentially that whatever is disseparated is conditionally independent in the data. And so the idea is, here I'm just giving you just a short intuition. So if you have two variables, X and Y, these variables are deconnected, which is the opposite of disseparated. If there is a path between them, so from X to Z to Y, that is unblocked. And that's how, in this specific case, in which we don't have any conditioning, unblocked just means there is no collider. So there is no structure in which there are two edges pointing together into the same variable, like this. And so we represent deconnectedness between X and Y with this symbol in red, so on the left. And we represent the separation with the other symbol on the right. And you see the symbol is very similar to conditional independence because we essentially assume that they're the same under the usual assumptions. And so we have also kind of more complicated cases as well. And in general, up to now, I've been talking about the unconditioned case. So we just have a path that is either blocked or unblocked. But in general, you can also block or unblock a path when you condition, or in particular, observe certain variables. So in this case, in which you have a chain from X to Z to Y, usually X and Y are dependent, so they're deconnected. But when you observe Z, you essentially interrupt the influence of X to Y. And so X and Y now, if you know Z, they become disseparated, or in what we assume they're conditionally independent in the data. And the kind of weird case is when you have a collider, you get the opposite. So X and Y used to be independent, but when you observe the collider, you essentially like forming something that could be like seen as selection bias as well, if you want. So you form a correlation between X and Y, or a dependence, a conditional dependence between X and Y given Z. And so I'm not going to go too much into the details, but there is a very nice interactive demo. And since the slides will be online, you can just click on this link and you'll find the demo. And if you're curious about this separation, I think it's very worth to try and play with it. So now I'm coming back. So I'm talking about this separation. I'm talking about this separation because we can also do this with the domain variable that I explained before we can have in the graph. And why is this even useful? So it's useful because, okay, so now I'm going to assume the standard conditions. So I'm going to remove the D just for simplicity. And this is useful because the conditional independencies with this special variable D that represents the domain, actually they mean they're talking about invariances across the domains. So if you have the outcome or the label Y is independent of D, this means that the conditional distribution of Y doesn't change across the D. And if you have the label Y is conditionally independent of D given X1, then the conditional distribution of Y given X1 doesn't change across the different domains. And this is what we're looking for, invariances. And in general, the idea is that if you know how this separation works and you have the graph, you can always find like separating sets or sets of features which will essentially transfer from one domain to the other. And so that allows us to reason about invariances in a principled way. And one of the things that, since several people are starting to work on causality and domain adaptation, one of the things that people assume, and this was I hope a slightly less common misconception at this point, but it used to be a common misconception recently, is that if something is invariant across several domains, then it has to be causal. And that's not necessarily true, because it depends if it's invariant in which domains. So if you had something that is invariant across all possible interventions, then definitely that's true, it's causal, but not in general. And so in this case, I have just a graph, and we can have a chat about it, essentially showing that X2 is, so both X1 and X2 are making the label Y invariant of the domain D, but this doesn't mean that X2 is a parent or a cause of Y. In this case, actually, it's a child. And so invariant features across many different data sets depends how are they different, these data sets. And so we generally need more assumptions. And I think this is something that was mentioned in the RM paper, but it wasn't very clear to the people who have followed the work. So I wanted to just underline it. And so there is another work called invariant causal prediction, which actually finds features, a subset of the parents. And in this case, you have to do something smarter. So you need to do an intersection or avoid the conditional independencies of Y and D given a set S. So you have to find a set S that is in intersection of all of these conditional independencies. For example, in the case above, you have Y is independent of D conditional on X1. So we have X1, and Y is independent of D conditional on X1 and X2. And so the intersection of X1, X2, and X1 is X1 itself. So in this case, it works. But sometimes it can be, this method can be too conservative. So it doesn't find generally all of the parents. It finds a subset of the parents. So in some cases, like in this case, it doesn't find any of the parents. So it's a high precision method and low recall. And there is another misconception, and this is maybe possibly a bit worse, is people think that in general, okay, I just take the causal parents and then, you know, I'll be always fine. And any intervention that happens, any kind of domain shift, the causal parents will protect me against that. And that's true, but not under latent confounding. So if there are some hidden variables, a hidden common cause between x2 and y, which we represent with this bidirected edge, then x2 is not anymore a good, a stable predictor of y because it's biased. Instead, one should use x1, and in this case, it looks a bit like an instrumental variable, so I guess it makes sense for a lot of you, that you should use x1 to predict y, and x1 will transfer across the domain. So y, the probability of y given x1 is invariant, y given x2 is not. And so this is some of the things that people in machine learning are kind of some common misconceptions they're encountering. And so the conclusion here is that causality, or in this case, using the causal parents of y, is neither necessary because, you know, you can still use things to predict y which are not parents, and also it's not necessarily sufficient if you have latent confounders. Like in this case, they're not, the parents are not enough for transfer. So instead, we want to use some other definition. And in this case, I'm actually going to talk about some of the, so this is a set of things that I would like my, let's say, causality-inspired domain adaptation method to satisfy. And obviously, spoiler alert, it's a biased list, so obviously we satisfy all of this in the end, but let's go through them anyway. So one of the things is we have, in some cases, the graph between x and y is assumed to be known. So we want to assume that we don't know the graph. So there is a graph of how the features and y are connected in the different domains, but we don't know it. We just assume there is a certain graph. We allow for latent confounders, which is something that very few methods do. And we try to avoid parametric assumptions. For example, a lot of methods assume linearity. We try to not assume that, and we delegate these assumptions essentially to the conditional dependence tests, which in some cases assume linearity, but they don't need to. And another thing that we do, which is similar to what was shown by Joris Moy in the talk on joint causal inference, is because we actually do end up using joint causal inference, is instead of modeling the changes between each domain, so instead of modeling the changes between each domain with the domain variable, we use context variables so that we can distinguish the changes between the mixture of the sources and the target. So the target is singled out. So we have some, essentially we instead of having indicator variables for just one for each domain, we have several indicator variables for each type of domain. Maybe this is a bit better explained when I showed some examples. And another thing is we want to avoid an assumption, which has been made by some of the methods, that if something works, if a set of features X works across multiple source domains, then it will work also in any target domain. So instead, we want to focus on things that are invariant in a specific target domain. And so this is also something that is assumed by methods that think that if something is invariant, then it means it's causal. And so here I'm going to just restate the problem a bit, and we call it causal domain adaptation in our 2018 paper, but in practice, it's just unsupervised multi-source domain adaptation. So it means unsupervised, we don't have labels in the target domain. Multi-source is we have multiple source domains potentially. We don't need to, but we can. And similarly to some of the related work, we interpret the change in the target domain as a soft intervention. And so it's just a change in the conditional distribution of whatever is the target of the intervention given its parents. And an important thing that we have to assume, because we cannot do this in general, is we assume that the label Y is not intervened upon directly in the target domain. Because we never see Y in the target domain. So if it's intervened upon directly in the target domain, we would never see its change. So we cannot do that. But this doesn't mean that the distribution of the label doesn't change. It changes, but mediated through the features. And so we're using this framework called joint causal inference from Moy et al. 2020. And there was a whole talk on this framework a few months ago, if you're very interested. But in general, I'm going to very much simplify it here. And the idea is just, instead of having one domain variable, we have several context variables, and we have these different distributions, and we put them together in a single table, like assuming they come from a single distribution, and we just have C1 and C2, which are context variables. And if we know something about interventions, we can encode some domain knowledge in C1 and C2. And if we don't, we do the simplest thing, and we just use them as indicator variables. So C1 is 0 in all of the datasets except in the dataset 1. And C2 is 0 in all of the datasets except in dataset 2. So they're very simple variables. And we're doing this because we want to represent everything together with a single unknown causal graph. And the ideas here of joint causal inference, again, I'm going to very simplify it a lot, but you can always see like the joint graph in the different domains is just the union of the graphs in the single domains. And these graphs could be potentially also different. So we could have x1 causing y, and x2 is disconnected in one domain. And in the other domain, we have a chain, x1 causing y and y causing x2. And when we put them together, we get the result on the right, in which we have also an arrow from y to x2, because they're a union of both of these graphs. And the context variables are just modeling the differences between the data sets. So in this case, one of the differences is that x2 is suddenly dependent or independent in the two data sets. So the C1, the context variable C1, has to represent that change. And in general, in joint causal inference, and Joris has talked about it a lot, we also allow for latent confounders, and also in general cyclic graphs. And in this talk, we're not going to talk about that. But if you're interested, this is one example of a cyclic graph. If you have x1 causing x2 in one domain and x2 causing x1 in the other domain, when you put them together, they look like a cycle. So going back to domain adaptation. So we want to, actually the idea of joint causal inference still is you put all the data together, and then you do essentially any standard constraint-based causal discovery algorithm. So what you do is you do these conditional independence tests. You treat the context variables as random variables. They aren't, but I think we can, so there are some assumptions to make it work essentially. And if you add also maybe some extra knowledge, for example, you can add some knowledge that the context variables are not caused by the variables, the system variables, so x1 and y and x2, then essentially we can get something like a Markov equivalence class of graphs in this case. And now I'm going back to the causal domain adaptation, because I've been talking about joint causal inference for a while, just to summarize it. So for simplicity, I'm going to talk about the very simple case in which we have only one source, one target. We assume we know the causal graph. And now this is just an example to show you which kind of variables we want to select. So let's assume we have this graph, x1 causing y and y causing x2, and a context variable c1 causing x1 and x2. So shall I use x1 to predict y, or shall I use x2 to predict y? And so what we're looking for is something that, again, other people have defined before, and I think people are continuously defining again. You can call them stable features, separating features. In the end, there are sets of features that deseparate y from the context variable c1, or the domain variable in a case in which you have a domain variables and not context variables. And so in general, they're the subset of all of the features for which the covariate shift assumption actually holds. And so here I'm trying to show, if we have plotted y on the y-axis and x1 on the x1 axis, so we choose x1 to predict y, and we have all the data in the source domain. So these are the green data points. And let's say we fit a line, like something super simple. We just do linear regression, we fit a line. You can see that the line will also work for the target points. So essentially the distribution is the same in the source and target, the conditional distribution of y, conditional x1. And this is something that if you know this separation, you can see from the graph, because you can see that there is a path from C1 through x1 to y. And when you condition x1, you can block that path. And there is another path growing from C1 through x2 to y that is blocked because x2 is a collider. So that's why this separation is very useful. And in this case, instead we try to pick x2, and if we pick x2 and we fit our line on the green dots on the source domain, it's completely wrong for the target domain. And in our case, we also wouldn't even know that, because in practice, we have an unsupervised domain adaptation case. So we'll be very wrong without even knowing it. And if you do have the graph, this is very simple to see, because there are two open paths. So both C1 through X1 to Y is open, and also X2 is a collider. And when you condition it, you even bias it even more, you open even more the path. So X2 is a very bad choice. And if we know the graph, we can see that. And so X1 is a separating feature set in this case, and even X1 and X2 together are still biased and could lead to an arbitrary large error. And these separating features, they don't need to be parents of Y, so they don't need to be causal. For example, we can have an X3 here, and X3 is still a good feature, a stable feature, separating feature for Y. And so this is like, I'm essentially just restating something that has been rediscovered a few times in the past. And now the most interesting question is, okay, you know, we just use the causal graph and we know which features are good and we can transfer. But what happens if we don't know the causal graph, which is the context of this paper? So one idea is, okay, maybe I can just do the conditional independencies, right? So we set conditional independencies and this separation are the same. I can just run conditional independence tests and find which feature is good. And that would be okay, I guess, but in our case, we have the unsupervised domain adaptation case, so we have 0 labels in the target domain. So Y is always missing when C1 is 1. So we cannot test this because it's essentially unknowable how the distribution of Y conditional X1 changes, because we never see Y in the target domain. So it's not missing a random, it's missing in a very specific way. So the general idea of the work we did was instead, what happens if we use all of the other conditional independence tests? So what happens if we know that X1 and X2 are dependent across, even in the mixture of the two distributions? Or what happens if we know something about X1 and X2 still being dependent, even if we take in each data set separately, etc. And so in order to be able to make this work, we had to make some assumptions. So one assumption that we made, because we were using a previous version of joint causal inference, is that there is an acyclic causal graph that feeds the data. Another assumption I had already mentioned is that Y cannot be intervened upon directly. And then there were some technical assumptions which boil down to saying that there are no extra dependencies that involve Y in the target domain, because we don't actually see Y in the target domain. So they cannot be extra dependencies involving Y because we wouldn't be able to recover them. But there can be extra dependencies not involving Y, so with the other features essentially. And essentially, this is a bit of an idea that this doesn't mean that we actually assume anything related to the separating feature sets. And so we had an example in the paper, and if you're interested, we can look at it very quickly. And essentially, you can do it by hand. Oh, okay, sorry. You can do it by hand by just using like 3 conditional independence tests. If the conditional independence tests have this result with the assumptions, you can show that there is a set of graphs that fit these conditional dependencies, and we can represent it with a summary graph like this, in which the dotted lines are just, they could or could not be there as causal relations. But the important thing is that even if there are several graphs, so we haven't identified the causal graph, in all of them, we can prove that untestable conditional independence, so that Y is conditionally independent of C1 given X1, it's true in all of them. Because Y is disseparated from X1, Y is disseparated from C1 given X1. And this is true in all of the graphs. Either there are the dotted lines or not, in all of them, this is true. And so here it's like a small point I wanted to make. And one of the things is that people assume that if you have invariances in the source domains, you can just assume away that this will work in the target domain if you have several source domains. And that's not true in general. So in this case, we have essentially on the left, we have, let's say, several source domains. So in this kind of yellow rectangle that represents 2 source domains. And in all of them, essentially, both X1, X2, and X1, X2 together are conditionally independent, make Y and C2 conditionally independent, but this doesn't mean that they are actually transferable in the target domain. And so this is a bit intricate, but if you're interested, we can have a discussion on this. And so in general, the idea of our work was not just to use the data from the source domains, but also to actually reuse the data from the target, the data from the features that are in the target, in order to learn what is invariant across essentially from the source domains to the target domain. And so in the end, this is the algorithm that we proposed. So we had a query. So we want to query, for example, if X1 is a separating set of features. We have some assumptions. We have all the conditional independencies from data that we are allowed to test, so the ones which don't have missing data. And then we use some work from Hittin and et al. 2014, in which they encoded this separation in logic, because this allows us to use essentially a theorem prover, and the theorem prover gives us 3 types of results. It can tell us, X1 is probably separating, so it separates in all possible causal graphs, or it's probably not separating, so in all possible causal graphs, it's a bad predictor, it's biased. Or in some cases, and this happens empirically in 30% of the cases, it actually abstains and said, I don't know. Because in some of the graphs, it works. In some of the graphs, it doesn't. I'm not sure which is the correct causal graph. And actually, I don't have interest in finding that. So I'm just not going to answer this question. And so we use this, essentially this setup of proving which features are separating in something we call a causal feature selection method. It was a very simple brute force type of method, but we just wanted to see it used in practice. And so in this case, we had like a standard feature selection method, random forest in this case, and we generated subsets of features, and we ordered them by the ones which were performing the best in the source domain. For example, we could have X1 and C2, or X1 and X2 and C2, etc. So these were the subsets of features. And then we tried to query the theorem prover in a very brute force way, because it was more a proof of concept. And we tried to find which of these sets of features was probably separating. And let's say we did find probably separating set A, then we trained the model f of A, again with random forest, and we use it. So we train this model to predict Y on the source domains, and then we apply it on the target domains, essentially. And then we had some results on some simulated data. And on the simulated data, our method was essentially improving the generalization loss. We had some results on the real world data, and that's why I was talking about all these mice. So there was a CRM causal inference challenge in which we applied these methods. And in that case, there were very, very small sample data. So we had around 13 mutant mice for each gene knockout and 400 essentially observational mice. And we had only 16 phenotypes. And so in that case, we tried to do something we called causal cross-validation. So we selected 3 phenotypes and 2 knockouts. And we generate a lot of data sets randomly. And then we try to see if we can reconstruct randomly one of the 3 phenotypes from the others, given all of these kind of source domains. And this is a bit disingenuous because I wrote the desiderata. So we do fit a lot of the desiderata. And actually, all of this we fit. So this kind of unknown causal graph, changes between domains, we fit it because of the use of joint causal inference. And the last 2 we also fit, and we fit because of the way we apply joint causal inference in our kind of unsupervised domain adaptation set. And one important thing, and this is, I think, more important than the method itself, is we didn't need to find the causal graph or even the equivalence class. We don't care, we're searching for separating sets. So essentially a conditional independence. And I wanted just to point out some other methods which use a similar idea. So Joris is here. So in his group, they have been working also on causal discovery for essentially causal bandits. And in this case as well, they don't need to find the causal graph or the causal equivalence class, but they just need to find a separating set. And so this is, I think, a very powerful idea. And then just to finish up, since I've been talking a lot, I just wanted to mention some applications of this method. So up to now, I was talking mostly about theory, but we have a new project with the MIT IBM Watson AI Lab. And so it's about cross-species translation, specifically for vaccine treatment. And so it's with this several people from MIT and from IBM. And the motivation there is that essentially only 10% of the drugs that are developed and they're successful in the preclinical studies. So in mice, only 10% of the drugs that are successful in mice actually work on human too. And so we want to improve essentially this development pipeline for drugs, right? And the question is, how do mice connect to humans? And one of the PIs of this project, Douglas Raffenberger, wrote this science article in which he's arguing that while most of the current approaches focus on commonalities, so genes that are, I think ortholog is named, essentially genes in mice that have similar behavior as genes in humans, and you focus on commonalities between the two species. Instead, in this case, we want to do something computational and want to try to use these domain adaptation approaches. And among these approaches, because I'm in the project too, we are going to use it for an unsupervised domain adaptation setting, in which we have different mice and treated and untreated mice and possibly also monkeys. And we want to predict a certain outcome on humans. And so the idea there is that we will simplify and assume that there is some kind of mapping between the different features of the species. And we essentially use this domain adaptation, causal domain adaptation setup that we wrote about in 2018. And we're going to use a theorem prover and find which of the features are translatable and which are not. And so this is the last slide. And so I'm going to step back a bit. And so I told you about how fantastic our method is, and all the good things about it, but obviously there is still work to do. And so there are some limitations of the methods. So one of them is that potentially it's a bit too conservative. So you could throw away sets of features which are very predictive because you cannot prove that they are essentially transferable. So it can be a bit too conservative. And so one of the things I think we can think about is how can we use active learning or intervention design to maybe decide which are some informative interventions in order to find the separating sets of features. And another thing that it's maybe more related to kind of more deep learning style machine learning is at the moment, it doesn't really use transformational features because there are some kind of technicalities with determinism. And so one of the questions is how can it use transformations of features? And the most important limitation of the approach is its scalability. So as a lot of causal discovery methods, also this method is not very scalable, especially the methods based on logic, unfortunately. And so the question is how to make it more scalable and how to be maybe a bit less pedantic or a bit less correct and use approximate algorithms, or how to combine it with low dimensional representations in order to make it more scalable and actually applicable to more real world cases. And the last thing we're working on at the moment with Wei Huang from CMU is we're trying to apply this to multitask reinforcement learning. These are in general, these kind of ideas. So if we have factored Markov decision processes, how can we use these kind of ideas to transfer the policy from several source domains to a new target domain? And that's it. Thanks.
Thanks, Sarah, for a great talk. Guillaume, do you want to take some questions?
Yeah, let's maybe ask a few questions. So one question that Richard asked was, so let me read it. So, yeah, so when you use the word test, what do you mean with real data? Is it kind of an eyeball test or a formal statistical test? And if the latter, what additional assumptions do you need to make?
You mean a conditional independence test or like,
yeah.
Okay, yeah. Yes, a conditional independence test. So in practice, in a lot of the cases, we used partial regression, or, like very simple. We assume it was linear Gaussian, so that's what we used, partial correlation. So, but in general, you could use any kind of statistical independence test.
Okay, makes sense. And so one additional question that I had was, do you so based on the limitation that you laid out, do you have a sense of when it is going to be conservative? Like what type of graphs is it going to work well for, and what types of graph is it going to not be not work so well for? And do you have the sense of which one is maybe prevalent in real world settings, or which one would you expect real world settings to look like?
Oh, okay. I guess it depends on also how many different environments you have. If you have a lot of environments, then I think it wouldn't be that much conservative, because it's if you had all of the interventions, you should be able to actually find the parents, and therefore it should be very easy to find separating sets. So the more experiments you have, the better it is. But otherwise, I haven't really thought about it. But maybe one of my co-authors may want to answer. Maybe not. That's fine.
I think they're busy answering questions.
Yes, exactly. Yeah, they seem busy. Okay.
Okay, so maybe we can move on to the discussion and then take questions back after that.
So stop sharing, right?
Yes.
Okay.
And then Dominik, whenever you're ready, feel free to start.
1 second. Can you see my iPad?
Yes.
All right, perfect. So thank you. First, thank you, Sarah, for a great talk. It's fun to discuss this kind of work. Yeah. So this talk actually had 2 titles. The other one was ask what can ideas from causality do for machine learning, and I absolutely love that question, because often people think about what machine learning can do for causal inference, and but there's also lots of stuff that can be done in the other direction, and this is an example of that. Okay, so we saw today domain adaptation. So we saw how causal inference can be used for making robust predictions, and I just want to quickly take a step back and motivate that again, at least intuitively, why this should be possible. And the example that I brought today is Mayan astronomy. So the Mayans, they were extremely good at predicting astronomical phenomena, and that was due to their religion. They wanted to know at which point a certain star would appear, like on their sky. And so they had tables, they had certain ways of doing that. They had like these devices where they looked at shadows. But like the way that they did it was very particular to the location and to the time at which they were doing it. So if you would have taken their tables and their ways of like their methods to figuring these things out, and you would have gone to Europe or to some other location, their whole prediction model would have like fallen apart. And the reason for that was that what they thought was that the Earth is in the end is the center of the universe and fixed. So they somehow had a wrong way of looking at things. If they would have known that the Earth evolves around the sun, and if they would have had a better model of that, then they would have been able to make predictions that actually work everywhere. So if you make non-causal predictions, or if you don't take into account the causal structure of a problem, then whatever predictions you might make might not be transferable, might not work in a different location. And you can also make that a little bit more formal, and that's what people have done over the past. So you can show that if you have a causal model, then you get an invariance property. The probability of the distribution of y given its parents is invariant across distributions, where here I'm looking at distributions that arise from interventions on covariates, and I also additionally assume that there are no hidden variables. So in some ways, causal models are extremely robust across distributions in a certain way. So now you can ask, well, okay, well, does that mean I should only make causal predictions? And Sarah says no, and I completely agree with her there. So causal models, and that's the point that she made today, they can protect against too much, and there are also cases where they actually protect against too little, because they are robust against all distributions that arise from interventions on the target variables. The problem that we looked at today was we want to predict on some target domain, which might be similar in some sense to actually, and will probably be similar to the source domain. So not everything will change. So we don't want complete invariance, but we have some sort of a targeted invariance problem. And that's what we formulated today. We want to find a separating set, the set x tilde, so that the distribution of y given x tilde in the source domain is the same as in the target domain. Because if we have that, that would mean we can just simply train a prediction model here and use it here without completely messing up our predictions. So instead of complete invariance, we want some sort of targeted invariance. Okay, so now if you want to search these sets, there is an issue. And the problem is that the target variable is not observed on the target domain. So I cannot actually test this relationship directly. And now there's this proposal by Sara and her co-authors, which is a combination of different ideas. And she says, well, we can assume that any conditional independencies that involve y in the source domain also holds in the target domain. And I can also assume that C1 does not have a direct effect on y. And in that case, I can do a lot more. Because then using that joint causal inference framework, I can infer some separating sets. Not always, sometimes I will not be able to tell anything, but usually, in some cases, I will be able to infer the separating sets by feeding the observed conditional independencies. So I use some conditional independence tests on the source domain into a theorem prover. Okay, and then in the third step, once I've found some of the separating sets, I can now also search for the one that has the lowest prediction error on the source domain to make sure that I'm transferring a model that has a good prediction performance. Okay, and then I can apply this on the target domain. Okay, so that's kind of roughly the workflow that we saw today. And like this is great for a couple of reasons. So like roughly these are the advantages. There are also other advantages, but these are the main ones in my opinion. So the first one is we do not really need to know much about the graph. We do not have to estimate it. We also do not have to make any parametric assumptions. So we can just use any random forest model or whatever we want to use as a prediction model. We're kind of not limited there. What we will get out of there is much less conservative than if we would just make a causal prediction. And what we saw today was that sometimes we will use the children. Sometimes we even might use not use the parents of the target variable, which first is unintuitive for someone trained in causal inference, but there are definitely examples of that. And in the end, and I think this is super important, the final model is tailored to the target distribution. So we're really kind of focusing on the task at hand, not just trying to do some like arbitrary invariance that might not work off too well. Okay, so that being said, like in the next few slides, I want to kind of like investigate a little bit, kind of in which cases we want to use this. And for that, I brought like a super simple example. I actually assume for now that the graph is known, so we have some background knowledge, and this is also an example that Sara used in her slides. So here I have my indicator of whether I'm in the source or in the target domain. I have a covariate x1 that has an effect on y has an effect on x2. And then I have a very simple structural equation model that I put down. Now, I also have a parameter t that essentially tells me how much the distribution shifts between source and target domain. So if I make this t large, there will be a large shift. Now, if you look at the probability distributions and at the conditional probabilities, you're going to see there's an y given x1 is invariant, of course, and y given x2 and x1 is not. So if you want to use a separating set, you would use this one. Okay, but let's now plot the error of what happens if you actually do not use the separating set. So here on the x-axis, I have the perturbation strength, so how different source and target domain are, and on the y-axis, I just have the mean squared error. And here the green one, that's the separating set, and x1, x2, that's just using everything essentially and just completely ignoring the shift. And what you're going to see is that if you have only a small shift, then using all information possible and ignoring that will actually lead to smaller prediction error. But then if you the further you go away, at some point you will cross the threshold, and using the separating set will be better. So in some ways, and that is also intuitive, the separating set does not pay off if you have small distribution shifts. And that, I think that holds for many of these methods that we're doing here. So the thing is, you're essentially buying insurance, and buying insurance does not always pay off. Buying insurance only pays off if there's a bigger difference. And I think that also kind of has practical implication, because it may make these methods difficult to tune, right? You do your conditional independence tests, and you could do the independence tests with a different threshold, getting different separation sets, and some of those separation sets might now have a drastically smaller mean squared error than the others. So there is a bit of a trade-off between kind of how invariant you try to be, how strict you are in the stage where you select the separating set, and kind of how well you do later. Yeah. Yeah. So let me just quickly put out some questions here. I really like this work. I like the general direction. I think there's lots of cool stuff that can be done. So yeah, the main one that I have, but that's also a question I have with most of the other stuff in this literature. How can we actually make sure that this insurance that we pay pays off? So can we somehow test or have some checks to make sure that the distribution shifts are large enough so that this protection is actually something that we should do? That also means, how should I choose the tuning parameters in this method? Or that also means, how do I choose how many source domains I actually kind of put into the whole problem? And another one is, now you have a robust model. Can we somehow communicate what we are robust against, right? If you have a graph, maybe it's easy to describe what kind of distribution shifts we are now robust against. If you don't know a graph, that seems to be a lot harder. But it seems like in practice, some practitioners might want to know, okay, this is a robust model. What can I do with this? Where else do you think this will work? And the last one, and this is not just a question for Sarah, I think that it's also a bit a question for everyone here. So Sarah asked, what can ideas from causality do for machine learning? And you can also similarly ask, what can ideas from causality do for generalizability and replicability of statistical findings? Because also there you want some sort of invariance. Sarah looked at invariance of predictions, but if you want to replicate findings, you want invariance of estimator and invariance of certain effects. So I believe also there, these separating sets and similar concepts are very important. And I see some work in that direction popping up, but I think it's still understudied, and there's tons of other cool stuff that can be done. Yeah, anyways, that's my discussion. And yeah, I want to hand it back to Sarah and her co-authors if they want to respond. Great work.
Okay, thank you very much.
Thanks, Dominik. Yes, Sarah, if you want to respond.
Okay, I know the questions, but yeah, essentially, I think, so I was very interested in what can we be robust against, so the middle question. And that one, I had an idea that maybe there is something that can be done even with the theorem prover in order to kind of try to see which of the interventions you can be robust against. So that's something I think that is a very interesting direction of work I haven't thought about yet. So thank you for the suggestion. And for the first one, I'm still, it's a bit more difficult for me to think about it. So the first question was, how can you know it pays off to use separating sets as opposed to non-separating sets? And I think in that case, it's a bit more difficult. So that's something, was that the question, right? I think.
Yeah.
Okay. That's something I still don't know yet about what would be a good idea. And also in our setting, we have an unsupervised domain adaptation case. So we assume we know nothing about the variable y in the target domain. So in that case, you cannot really do much, but maybe you have some domain knowledge that you could use.
Yeah.
So that needs to be investigated as well.
Yeah, I totally agree with you. I think with the current problem statement, you will not be able to do that, but making additional assumptions or having some additional background knowledge will probably allow you to target that.
So sounds good. And maybe some of my co-authors want to add something, let's say Joris or Tom or Thijs. No, let's say no. Okay.
I was just answering a question.
okay. They're too busy. Okay, that sounds good.
All right, so maybe we'll wrap up. So
sounds good.
Thanks, Sarah, for a great talk, and thank you, Dominik, for a great discussion. Let me just share my screen. So next week, we're going to have Corwin Ziegler from the University of Texas at Austin. He will tell us about bipartite inference into air pollution transport, estimating health effects of power plant interventions. We're looking forward to that talk, and we hope you will join us. Thank you.